Okay, so this is practice review session for going over the practice exam spring 2022. Okay, or sorry, spring 2020, not 22. Okay, so first question, it says consider this vector field and they give you this path given by a unit circle in the plane oriented counterclockwise. And they say, what is the work done by F across gamma? So as soon as I see this wording, what is the work done? And then part B, it says, what is the flux done? That should make you think of probably like Green's theorem, because we know there's two versions of Green's theorem, like the circulation version and then the flux version. So when I see work done, I'm going to think Green's theorem. Okay, and so what does Green's theorem say? You should say that, oh, I'm going to use Green's theorem, and then you can write the formula, which is the integral over some boundary of m dx plus n dy equals the double integral over your entire region, like the domain interior, where you have partial n over x minus m over y, x dy. Okay, so now we look at our field. Our field y squared is m, x plus 2y is our n. And so when I follow Green's theorem, I should get the double integral of partial of n with respect to x is 1. Partial of m with respect to y, that gives me 2y, right? Dx dy. Now I could keep this question in polar coordinate or in Cartesian coordinates. So meaning what is like my curve? What is my path? My path is a unit circle. I can draw my unit circle. And we usually parameterize it with like cosine t and sine t. So I could do that. Or if I don't want to keep it in Cartesian coordinates, what happens if I convert to polar coordinates? Because I have a circle, so let's do polar coordinates instead. So I'm going to convert to polar. What does converting to polar means? I have to first change my bounds. What should my bounds be? We have r goes from 0 typically, and it goes to the radius. What is our radius? We have a unit circle, so the radius is 1. Then we have our theta bounds. There's no limit at all for our circle. It's our entire circle. So theta is 0 to 2 pi. Okay, and then second, I need to change my integrand. What is the parameterization I'm going to use for my circle? It's exactly this, which is cosine t sine t. So when I substitute my parameterization into my integrand, I have 1 minus 2. What is y? Y is sine t. And then, or I could say sine theta, if we like thetas instead. And the last thing I need to do is convert my differentials. The dx dy, when I convert to polar, it becomes r dr d theta. And we want to be careful about the parentheses here. Okay, so now we have that, and we can actually now compute our integral. So we have 0 to 2 pi. This rewritten, r equals 0 to 1. If I distribute r, I get r minus 2r. Oh, sorry. For my parameterization, I should clarify that I should have used r cosine theta, r sine theta. I have an r. Sorry about that. Okay, so continuing, I have 2r squared sine theta dr d theta. So when I integrate with respect to r, I get r squared over 2 minus 2 sine theta, because that's like a constant, r cubed over 3 from 0 to 1 d theta. So that gives me, when I plug in 1 for r, I get 1/2 minus 2/3 sine theta And when I plug in 0, I get minus 0 minus 0. E theta. Now I integrate with respect to theta. So I get half theta minus 2/3 cosine theta. Negative sign comes out. 0 to 2 pi. And so that gives me 2 pi over 2 plus 2/3. Cosine of 2 pi is 1. So that was just plugging in 2 pi. Then I have to plug in 0. So I get 0 plus 2, cosine of 0 is still 1. So I get 2/3 times 1. So that gives me a final answer of pi plus 2 pi thirds minus 2/3 or pi. Okay, and part B says what is the flux across gamma? So there's either you can memorize the formula or you can derive the flux formula from Green's theorem. The formula for flux says that the flux, in other words, integral over the boundary of m dy minus n dx equals, so I still want to say I'm using Green's theorem. That equals double integral over the interior domain of m over x plus n with respect to y, dx dy. Okay, so when I take m, what is my m? That's y squared. The partial with respect to x is 0. I get double integral of 0 plus, what is my n? That's this. And the partial with respect to y is 2. Okay, plus 2 dx dy. And so I get 2 integral of dx dy. What is the integral of dx, double integral of dx dy? That's the same as the area of a circle. What is our circle? We have a unit circle, meaning it's a circle of radius 1. So the area is pi r squared, where r is 1 because it's a unit circle. So our final answer is 2 pi. Okay, so I have a question in the chat which says, for part A, does it matter if you include the r in the parameterization? Since we know it's a unit circle, I just left it as is and I still got pi. So I guess you can substitute r for 1. Could you also solve for work by using a path integral instead of Green's? Yes, you can also do a path integral instead of using Green's, and you should get the same. So doing it the path integral way is like you have your function, you plug in your parameterization, and you dot it with the derivative. So that should also work. Okay. Yes. B work. So part B, I used Green's theorem for the flux version, and that was this formula. I did the partials, and I get 2 times the area of a circle. And we have a unit circle, so the area is pi r squared.
No, I don't get it.
Radius of 1.
Why? Quarter white, a quarter Indian.
When can you use path integrals? How did you know you could use it here instead of Green? So you can always use path integrals. That's the longer way, but we know that using Green's theorem is like a shorter way instead of like actually doing all that work. And so instead of doing the path integrals, I can use Green's theorem. Okay, and the path integral method only works for flux, right? It should work for either work or flux. Is there a way we can get access to these questions? It should be on Canvas. It's labeled 2020A, like at the very bottom of the Canvas modules.
Wait, Iris, if you're going to use the path integral, how do you find the work and the flux? Like, how would you set it up?
So for path integral, yeah. So you would find the parameterization, which is r cosine, r sine, and then I guess in this case, our radiuses are 1. And so we would take the derivative, get negative sine theta, cosine theta. So when you do this integral, you would plug in your parameterization into your function. So for y, I plug in sine squared. So I have sine theta squared. And then x plus 2y is cosine theta plus 2 sine theta. So that's my function, my field with my parameterization plugged in. Dot product it with these like hat things are telling you what you want to multiply by, like which derivatives. I should multiply by the derivative of the x component, which is negative sine, and the derivative of the y component, which is cosine d theta. And I guess theta would be 0 to pi. So that would be for work. And for flux, the only thing that changes is we have a different formula. So flux is mdy minus ndx. So that means when I'm doing the path integral for flux, I would instead have sine, I would still have this, my function with my parameterization plugged in, nothing changes. But what I dot product it by, this first thing should be the derivative of y, the y component. So I should multiply by cosine, and then the derivative of the other component, which is negative sine d theta. I haven't actually checked this. If this doesn't exactly work, you might have to multiply by another negative.
I'll leave it on because I would like to see as I go through the
Yeah. Okay, so let me. Okay, any other questions on parts A and B so far? Okay, yep. So this is part B. So we're using Green's theorem, and we plug these in, we get these partials, and we get 2 times the area of the circle. Area of a circle is pi r squared. Okay. Part C says, is F a gradient field? So how can we tell if something is a gradient field? We can only tell if it's a gradient field by using the component test. What is the component test? It's saying we should test all of the different partials and see if they're equal to each other. So here in the previous versions, whenever we were using component test, we were always checking like 3 things. Like we would check the partial of m with respect to x, with respect to y equals n with respect to x, and then m with respect to z equals p with respect to x, and then n with respect to z equals p with respect to y. Those were the 3 things we checked in the past for component tests. That was because our vector field was always in 3D, like we had 3 components for our vector field. But right now, because we only have an I and a j component, we don't have to check all 3. The only possible partials we can check are m with respect to the other variable, y. Is that equal to n with respect to the only other variable we have, which is x? So to see if F is a gradient vector field, we should check this. Is that true? Well, the partial of m with respect to y gives me 2y. Partial of n with respect to x gives me 1. Are they equal? They are not equal. And so it's not a gradient vector field because it doesn't pass the component test. Okay. Any questions on problem 1? Okay. Problem 2 then. Okay, we want to consider these functions. So f is a function of 3 inputs, 2 outputs. G has 2 inputs, 3 outputs. Compute the derivative of f of g at the origin. So when I see derivative of some composition, I think chain rule, because you have this composition and you're taking a derivative. So let's write what this means. Like they want you to find the derivative, so d, of the composition. So the derivative of the composition, if we want to evaluate it at some point at the origin, so write 0, first of all, should it be 0, 0, or should it be 0, 0, 0? Like, how do I know I'm plugging in the correct thing? Let's first look at our functions. So what is f of g saying? That composition means we start with g. G has two inputs, x and y. G then takes it to three things. Some like I'll just say something, something. So it takes it to an output of three things. And then F will take in those three things and output two things. So in total, this composition, F of G, it has two inputs and two outputs. This means that I should have only two inputs here. So I want to evaluate the derivative at the origin where I have two inputs. Then by the chain rule, this equals df at, this is important, this should be g of a, or is g of 0, 0, times dg at 0, 0. Okay, and so we have df at, what is g of 0, 0? Well, for that, I can plug it in directly from up here. G of 0, 0 is I get e to the 0 minus 0. That's e to the 0. 5 times 0, 0, minus 3 times 0 squared is 0. And then e to the 0 is 1. Cosine of 0 is 1. So that means g of 0, 0 is 1, 0, 0. Times dg of 0, 0. Okay, and now let's find what is df. So remember that when I'm finding the derivative matrix, or also called the Jacobian, the rows are outputs, columns are inputs. So I look at my first output, take the partial with respect to u, that gives me 4u. Partial of this with respect to v is -1. Partial with respect to w is 3. Okay, and then I look at my second output, partial with respect to u is 4v. Partial with respect to v is 4u minus 5w. And partial with respect to w is -5v. So we have that evaluated at 1, 0, 0. Now I need my derivative of g. So let me take that. I look at my first output, partial with respect to x is e to the x minus y. Partial with respect to y, now we have to be careful because when I'm taking this partial, I'm also doing a chain rule, right? I'm doing e to the something, which is x minus y, times the derivative of the exponent with respect to y. The derivative of x minus y is -1. So negative comes out. Then I look at my next output, partial with respect to x is 5. With respect to y is -6y. Over here, I have sine x, and then 2e to the 2y. So when I plug in these numbers, I get 4, -1, 3, 0, 4, 0. And over here, I have e to the 0 is 1. 5, sine of 0 is 0. I have a -1 here, 0, and 2. Okay, so I get that the derivative of my composition is this matrix here. -1, 2, 20, 0. Now part B says, if again at the origin, all the inputs are increasing at unit rate, at what rate are the outputs changing? So I see like a unit rate, and it's asking me what are the outputs changing at. So that reminds me that any matrix represents some rate of change of outputs with respect to the inputs. And so we have that idea that rate of change of outputs, it equals your derivative matrix times the rate of change of inputs. So that's what I'm going to do for part B. I'm trying to find my rate of change of outputs. I'll call it L for now. it should equal the derivative matrix in general times some rate of change of inputs. What is my derivative matrix I'm considering? I'm considering the derivative matrix of this, the composition. What was that derivative? I found in part A, it's this matrix. What should H be? That's the rate of change of inputs of my composition. They tell me the inputs of the composition are increasing at unit rate, which means they're all ones. So I should multiply by 1, 1. So I get 120. And these are the rates of change of outputs of my composition. Any questions on problem 2? Okay, problem 3. So we want to consider this matrix A and a vector B. First question, solve the system AX equals to B for X. Okay. So there's 2 general ways whenever you see an AX equals B problem, right? First way is you either do row reduction, or like you make a big augmented matrix and row reduce, back substitute as needed. Or you can multiply by the inverse. So X would be A inverse B. Now, generally, when this matrix is a big matrix, like we don't want to find an inverse of this because finding an inverse of this would still require row reducing anyway. So you generally want to use this if you have like a small matrix, like a 2x2 matrix, perhaps. But in general, if you have a big matrix, row reduction is the better way. So let's do row reduction. So I make a big augmented matrix, meaning I write my entire matrix. So 3, 0, 1, 0, -8, 2, 6, 2. And I could do this dotted line thing. And then I write my B vector. So 9, 6, 10, 2. Okay. Also, let me just write the general form first in case they ask you to like, what is exactly AX equals to B? Like, what does it mean? You can first write it out as this entire matrix A times X. X, they tell us, is this star, 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 star. Let me label them as X1, X2, X3, X4. And that should equal my B matrix. I know there should be 4 stars or 4 variables because in order to properly matrix multiply, the number of columns here should equal the number of rows here. Like I should be able to matrix multiply correctly. Okay, so from this system of equations, I get this augmented matrix, and now I row reduce. Question, is B a matrix or vector? B is a vector because it's a some number by 1. It's like a column vector. Yeah. Okay. So let's row reduce. The idea with row reduction is you want to always get like a 1 in the top corner. That's like the ideal solution. And so let's see, we have this 3 here. I don't want a 3 there. I want a 0 there. So what am I going to do? I said I can make row 2 be row 2 minus 3 of row 1. That means in my first row, I get 1, 2, 3, -8, 9. 3 minus 1, 3 times 1 is 0. So I got what I wanted. Then I have -1 minus 6 is -7. And then I have, this is 0 minus 9, which is -9. And then I have 22 and then -21. The bottom 2 rows, I can keep the same. Okay, so at this point, you can stop and back substitute if you want, which is what I'll do. Or you could keep on row reducing until you get zeros in all of these places. And if you do get zeros, like if you row reduce completely until you get all zeros here, then you'll exactly get x4 equals whatever number is here. X3 is this number, x2 is this number, x1 is this number. But say I didn't want to keep row reducing, I can back substitute. So the last row, I always start with my last variable, which represents what's in my last row. So my last row tells me 2x4 equals 2. So imagine this is like the x1 column, x2 column, x3 column, x4 column. So 2x4 equals 2, which means x4 equals 1. Then I look at my third column. That tells me that x3 plus 6x4 equals to 10. I just found what x4 is. It's 1 equals 10. So that means x3 is 4. My next row tells me negative 7x2 minus 9x3 plus 22x4 equals negative 21. So negative 7x2 minus 9, I just found what x3 is, it's 4. Plus 22, I just found what x4 is, it's 1. So it's negative 21. So I can simplify and I get x2 equals 1. And finally, the first row tells me that x1 plus 2x2 plus 3x3 minus 8x4 equals 9. I can plug in everything I've already seen. So I just found that x2 is 1 plus 3x3 I found was 4 and x4 I found was 1. So I can simplify and get x1 is 3. So my final solution is x1, x2, x3, x4 equals, what is x1? That's 3. X2 was 1, x3 was 4, x4 was 1. Okay, and another way of like remembering exactly, like how do you even get this, like why does this red, the second row mean negative 7x2 minus 9x3 plus 22x4? Like why is that? That's because think about what happens when you matrix multiply. Like if I took the second row and this column, when I matrix multiply, what do I get? I get exactly 3x1 minus x2. Sorry, because I row reduced up to like this line. Sorry, this line times x1, x2, x3, x4. Yeah, so you can think about we have 0x1 minus 7x2. That's where this comes in. Minus 9x3 plus 22x4. Okay, question. Does it matter if we put a vector in square brackets or the usual brackets? For your final answer, I guess it doesn't really matter. You can write it in like the circle of brackets. Also, does it matter if we write it horizontally or vertically? It doesn't matter too much. You want to be sure that like we understand that you understand what the solution should look like. So like if you just write it as 3, like make sure you indicate that it's a vector specifically with like this arrow. If you like want to write it horizontally, like we want to make sure you're showing that, you know, the answer should be a vector. Okay, and I'm also getting a question to show 2a and 2b real quick again. This was 2a and 2b. So yeah, 2a was like finding that derivative matrix, and then 2b was evaluating it at the rates of change of inputs. Okay, so back to problem 3. Part B says compute the determinant of A and write your answer below. So let's find the determinant of A, sorry. Okay, so let's record what we've done so far. What did we do? We took our matrix. So I'm going to copy paste what we just did. I'm trying to find the determinant of A right now. Okay, so I can ignore B because I'm not looking at B. I'm just looking at my matrix A. Okay, and we started off with the top matrix there. This is positive 22. So this is my matrix A. What did I do? I row reduced it so that I got to this upper triangular form. Now that it's in an upper triangular form, what's the determinant of an upper triangular matrix? I can multiply the terms on the diagonal. So I'm going to call my original matrix A. This is my reduced matrix R. In general, the formula is that to get back to the original matrix, the determinant of it, it's going to be the determinant of the reduced matrix divided by any changes that we made. So what is the determinant of R? I can multiply directly. 1 times -7 times 2 is -14. What were the changes I made? I only did a added combination. And recall that combination does no change to your determinant. So I just divide by 1. So my final answer for the determinant of A is -14.
Sorry, under what scenario would you not be 1? And if so, how do we find you?
Yes, so U is any changes that you make when you're row reducing. So when you were row reducing, if you switch to columns, if you do a switch, then you should divide your determinant by -1. If you do a multiplication by K, so if you multiply your row by K, then what you should do is divide by K. Divide by K. And if you just do a combination, meaning like some R number equals R1 plus something R something, then no change, or you just divide by 1.
If you switch 2 rows, does it cancel out and just become positive?
If you did row 2 switch with row 1, and then another like row 1 switch with row 3, then yes, you would cancel because you have negative times a negative.
Okay, thank you.
So
what if you multiplied a row by a number and then added it to another row?
So if you did like row 2 is 2 row 2 plus 3 row 1, that is not right. That's not considered a combination because you've changed your original row. So this is technically like you're doing 2 steps in 1. What you've done is you've done a multiplication by 2, and then you've done a combination. So that's why I recommend writing your row reductions as like your original row equals keep that original row and do some like change to it, whether it's combination or multiplying or switching. So if you did this is technically 2 steps. And so you would be dividing by 2 for your determinant. Okay. Question in the chat, if we multiplied a row by a scalar C, then U would be C. Yes. So what row reducing is doing is like, when you're multiplying by a whole entire row, it multiplies the determinant by that number. But our goal is to get back to the original determinant. So if you want to go backwards, that's why you do the opposite operation. You divide by that constant to get back to your original determinant. Okay, and another question, I thought you could only multiply diagonally if you have all zeros around the diagonal. So you can multiply diagonally if you have an upper or lower triangular matrix, or if you have a diagonal matrix. In both situations, you can just multiply the terms on the diagonal to get your determinant. So like if you have a matrix like 1, 2, 3, 4, 5, 6, 0, 0, 0, you can multiply diagonally. If you have a matrix like 1, 2, 3, 4, 5, 6, you can also multiply diagonally. And if you have just 1, 2, 3, you can multiply diagonally. Okay, and yes, there are also other ways. So question is, are there other ways to get the determinant here? This is our matrix A. You can also do minor expansion if you wanted to. And I think minor expansion is the only one that would make more sense. So minor expansion or row reducing. For minor expansion, you want to make sure you're choosing, like, don't do more work than you need to. Don't expand by the first row because that would be a lot of work. Expand by the last row because there's a lot of zeros here. So when you do minor expansion, you get 0 times this matrix, but 0 times anything is still 0. Then you get minus 0 times something, plus 0 times something, minus 2 times the determinant of this. Okay. So for minor expansion, you can choose, so question is, can you explain minor expansion? You can choose any row or any column. So for example, if I choose this last row, what happens is I get that the determinant is the first number, 0, times the remaining determinant. So I imagine canceling out that row, canceling out that column. The remaining matrix is this matrix. So I would multiply by that remaining thing. Minus the next term, 0, times the determinant of the remaining thing. And then I have another plus 0 times the determinant of remaining thing, minus 2 times the determinant of remaining thing. And this 2 term is the only one that really matters because you see that 0 times anything is 0. These will cancel out. Okay, and once you get to here, you can then do minor expansion again. Okay, if you replace row 1 with row 1 multiplied by 3, would I have to divide by 3 at the end? Yes. So the question in the chat is saying, if I did row 1 equals 3 times row 1 plus row 2. Again, this is, you're combining things together. So I would recommend writing things separate. Like, okay, I mean, you can do like combinations, just want to be careful. This is technically first a multiplication, multiply by 3, and then a combination. So my U is 3 because I multiplied by 3, and then I did a combination, so no change, times 1. So that's why I would recommend saying, oh, I'm going to do row 1 is 3 row 1. That way I know multiply by 3. Then I can say the new row 1 is now row 1 plus row 2. So that's a combination. Okay, is it
So
possible?
would you divide by 3 then?
Yes, you would divide by 3. So because what row reduction does is it multiplies your determinant, but we don't want like the determinant of the resulting thing. We want to go backwards. So that's why I'm dividing by whatever like I do. Okay, is it possible to only use switching and combination? Are there any cases where you would need to multiply by a row? I guess you don't have to multiply by a row if you, or like sometimes you might need to multiply by a row in order to cancel things out. But yeah, it just depends. Like you can use whatever row operations you want. Okay, so if you, another question, if you did row 1 minus row 2, what would it be? So if you're saying you want to change row 1 and do row 1 minus row 2, that's a combination. So no change. If you do row 1 is, so separate case, these are separate cases. If you did row 1 is negative row 1, I'm multiplying the row by negative. So that's multiplication by -1. So what you would do to get back your original determinant is you divide by -1. Okay, and another case scenario, if you did row 1 is row 1 plus 4R2, that's still a combination, no change. So a combination is always where you're keeping the row you have the same and you're just adding some multiple of a different row. That's a combination. If you make some fundamental change to the row you're considering, for example, multiplication or like a switching, then that's where you have different consequences, like this multiplication thing or a -1. Okay. Any other questions on problem 2? Or sorry, this is problem 3. Okay. And for a switch, do you multiply by -1? Yes. So separate scenario, if I did row 1, switch with row 3, I would multiply, like it multiplies the determinant by -1. So to get back to your original determinant, my U would have a -1 here. So I'm essentially dividing by -1. Okay. Question 4. And I did, like, I have all these rules written out in the review session notes as well. And those are posted. Okay, number 4. Consider the following parameterized curves in 3D. Okay, part A, compute the derivatives of the paths as velocity vectors to the curve. So when I take the derivative, right, that's taking the derivative component-wise. So part A, derivative of gamma 1. That means I take the derivative of sine t, so that gives me 2 cosine 2t using the chain rule. The derivative of t squared plus 2t is 2t plus 2. And the derivative of natural log, in general for chain rule, remember that natural derivative of natural log is the derivative of u over the actual u. So when I take the derivative of this, what's the derivative of the inner thing? That's -1 over the actual whole thing, 1 minus t. Okay, oh, I should put a prime here. Derivative of gamma 2. That will give me here, you have to use chain or chain rule again. So I bring the 2 down. So I have -2t minus 1. Don't forget to multiply by the derivative of the inner thing, which it turns out it's just 1. Derivative of 2t is 2. Derivative of e to the t is my favorite derivative because it's e to the t. Part B, these two curves intersect at the origin when t equals 0. Using part A, compute the angle at which they intersect. So I see angle, and I think of the formula. What is the formula for finding an angle? Right, that formula was always cosine theta is any two vectors dot producted divided by their scale, their lengths multiplied. So let's see. But in order to use that formula, right, usually we have an actual vector, like a vector with numbers in it and another vector with numbers in it. Right now, our velocity vector is just expressions. So once we plug it into this formula, it would be like a bunch of expressions. We don't get a number. Like, how do we fix that problem? Well, the problem is that we need to get actual numbers for our vectors. How do we get numbers? We need to plug in some t. And they tell us that the two curves intersect at 0. So let's use what they said and plug in 0 to get what is my first vector. My first vector is going to be 2, 2, -1. And my second vector is going to be 2, 2, 1. So I plugged in 0 to my velocity vector and 0 into my second velocity vector. These are now the vectors that I'm considering. I'll call this u and I'll call this v. So I'm trying to compute the angle at which they intersect. So cosine theta equals u dot v over its lengths. In other words, theta is what arc cosine of u, that's my gamma 1 prime at 0. V is my gamma 2 prime at 0 over the lengths. Gamma 1, 0, and gamma 2, 0. So we have 2, 2, 1, dot product with 2, 2, 1. That gives me 2 times 2, which is 4, plus 2 times 2, which is 4, minus 1. The length of u is square root of each of the components. So 2 squared plus 2 squared plus -1 squared. And the length of v is also 2 squared plus 2 squared plus 1 squared. So I get arc cosine of 7. This is 3 times 3. So I have arc cosine of 7 times 7 over 9. Okay, so question, is the derivative parallel or perpendicular to the original function? So I would say the derivative is tangent to your original function. So you have some plane, I guess, and the derivative gives you like two vectors on your plane. Why couldn't we have in t equals 0 for the non-derivative form? So, okay, so the idea is that right now they're giving us two curves. So this is like gamma 1, some weird curve. This is some gamma 2, some other weird curve. In order to use my formula, I need actual vectors, but right now these are like weird curves. I don't have any straight lines, like I don't have any vectors. So in order to get vectors, if I take, what does taking the derivative of this do? It finds like the tangent line. So this, the orange line would be like the derivative of gamma 1. And this red line would be like the derivative of gamma 2, where they're intersecting at t equals 0, right? So I have some weird purple curve, and I have some weird green curve. All I know is that they intersect at t equals 0.
Holy shit.
And so using that point t equals 0, I can find the tangent vectors by taking the derivative. And that's my orange vector, my red vector. And now I can use my formula. So that's what I'm doing. So what are we trying to find the angle between two vectors? Do we only use velocity vectors when the position vectors are 0 vectors, or do we generally use the velocity vectors to compute angle difference? Yeah, you're given like two curves. You take the derivatives to get their velocity vectors, because that will give you this orange, nice, like straight orange vector and this nice straight red vector. And then you can use this formula. So that's what I've done. I found those straight vectors or tangent vectors to my curve. And now I'm trying to find like, what is this angle here? That's the question. This is theta. Okay. Okay, and part C says, if we use two independent parameters, we could define a parameterized surface via this thing. But it says compute an implicit equation for a tangent plane to the surface at the origin. Explain what you're doing and show work. So generally, when you're trying to write an equation of a plane, we do generally use the implicit equation, like we want to use the implicit version of the equation. So that's a good thing that we are doing it, because think about when we're writing an equation for a line, we always use the parametric version. And if we're writing an equation for a plane, we use implicit. That's generally the rule we follow. How do you write an equation of a plane? Part C. I have some curved thing. And I'm trying to find the equation of this purple plane here. What are the things I need? I need a normal vector. So I need this orange sticking out vector. Because to write any equation of a plane, it's always going to be the normal vector dotted with x, y, z minus your original point equals 0. That's the equation of a plane. What are the things I have? Right now we have like two random curves, but I found the derivative vectors, the velocity vectors from part A. Those velocity vectors are exactly the things tangent to my surface. These red vectors. Those red vectors are the things I found in part A. So they are like tangent. They're on like the tip of my, like exactly on my surface. And so they're tangent to my plane. What do I know about these red tangent vectors? I know that if I take the cross product, I'll get a resulting vector that's orthogonal to both of these vectors. So if I take the cross product of my two red vectors from part A, I'll get a normal vector. What were my vectors, or my red vectors? They were these things. So this is my first red one. This is my other red vector. And so the orange vector, the normal vector, is going to be 2, 2, negative 1. Cross product with 2, 2, 1. What is that cross product? You can do the cross product lots of ways. You can either do it the determinant way, where you write ijk, and you write each of the vectors like this. Okay, let's just do it that way. So what do I get? I have 2 minus negative 2, that's the ith component, minus, I have 2 minus negative 2, that's the jth component, plus 4 minus 4, that's the kth component. So that gives me 4i minus 4j plus 0k. In other words, 4, negative 4, 0. That's my normal vector. So what does that mean for my equation of the plane? Equation of the plane is normal vector dot x, y, z minus some original point equals 0. My normal vector I just found, it's 4, negative 4, 0 dot with x, y, z. What is my original point? Well, I know that my vectors intersected at t equals 0 at the origin. So let's plug in the origin for my point. Is this point right here. That's the origin. That's where they intersected. 0, 0, 0. So that means I have 4, negative 4, 0 dot with x minus 0 is still x. Y minus 0 is y. Z minus 0 is z. So I have 4x minus 4y plus 0 z equals 0. So this is the equation of my plane. Okay, so question is, how might you convert from implicit to parametric and parametric to implicit? So I would say that for so for example, you have this plane and we can write it parametrically. What these vectors would be if you wrote it parametrically would be like, so we have s of t1, t2. You would say it's equal to some original point, which our point is 0, 0, 0, plus I take one of these vectors. So 2, 2, negative 1, and I write t1, like my first variable. Take the other vector, multiply it by my other variable. And you can convert, you can make sure that you're getting the correct thing by plugging things in. So this is saying like your x component is 2t1 plus 2t2. Your y component is you get something 2t1 plus 2t2. Your z component is negative t1 plus t1. And you can plug in those x, y, z's into here and see if you get something that satisfies it's equal to 0. That's how you can make sure that your implicit equations are like agreeing with your parametric equations. Okay, and our velocity vectors from parametric equations always tangent to the curve, yes. And so why is the velocity vector tangent to the plane in this case? Would you be able to explain what the surface is and how it relates to the particle? Okay, so summary of this question. Let me redraw my picture. Okay, we have two curves, T1 or gamma 1, another curve, gamma 2. They are curves in 3D. Now, if I have, so yeah, they're curves in 3D. If I take the derivative of gamma 2, what does the derivative mean? The derivative is like, I'm finding the tangent line. So the derivative of, let me make this, of gamma 2 would give me like this bolded orange line. That's gamma 2 prime. Gamma 1 prime would give me this bolded line. Let me draw it better. Like that. Gamma 2 prime. Because this is the tangent vector to gamma 1. So this is gamma 1 at the origin. This is the origin right now. 0, 0. Now imagine that these planes, these vectors, where are these vectors living in? They're living in 3D. So it's like, imagine I have some bottom curvy shape. Okay, so imagine I have like a globe. My two vectors are like crosses that are at the top of my globe. Okay, but I need a normal vector in order to find what is the plane. This is my plane. Okay, this is a very messy picture. So this is my orange vector, this is my blue vector. And they're living on my plane. I need to find the normal vector, which is this. I know that in order to get a normal vector, it's the cross product of any two tangent vectors that are living on my plane. So that's why in part C, I take the cross product of the orange vector and the blue vector in order to get my purple vector. So whenever you take like these tangent things, imagine they are living on your surface. This black thing is like a surface, like a globe. And my orange vectors and blue vectors are like this Apple Pencil here. And I'm trying to find my plane, the plane that my pencil is living on. So what is the surface in this case? So they don't really specify a surface, but we can imagine that there's like where this curve has to live like somewhere. So, I mean, this is just more to help you visualize that, like what this looks like. Yeah, so it's like the space where the two curves live. Yes. Okay. All right, any other questions on problem 4? Okay. And yeah, I would say this is a pretty common question. So it's like the reason why we have to do part B is because like you have these curvy things and you can't really find the angle between two vectors if you don't have actual vectors. If you only have curvy things, you can't really find an angle. So you need a straight like vector. And we get that straight vector by taking the derivative. Okay, part 5. So we have this vector field and it says, what is the divergence of F? So divergence, what is the divergence of F? Okay. We know that by definition, the divergence is always the partial of your first component with respect to X, plus partial of your second component with respect to Y, plus partial of your third component with respect to Z. What is my first component? That's this thing. Partial with respect to X gives me 3x squared. Partial of the second thing with respect to Y is 3y squared. And partial with respect to Z of the third thing is 3z squared. Okay, part B. Compute the flux out of F. Oh, sorry, compute the flux of F out of the sphere of radius 3 with outward pointing normals. Okay, keywords, I see flux. Whenever I see just flux of some vector field, I think Gauss. If you see curl of the flux, then you think Stokes. So I'm trying to find the flux of something, so that's Gauss. What else do I need? They're telling me I have outward pointing normals. Outward pointing normals is the usual direction we take. So we just use Gauss, and whatever we get with Gauss, that's our final answer. If the normals were pointing inward, then that's opposite of what we normally want. So you would do Gauss, and then at the end, take a negative of your answer. Okay, so what does Gauss's theorem say? You want to say, I'm using Gauss. You want to write your formula that you're using. And there's lots of different versions of however you want to write this Gauss's formula. Like that, for example. So I have triple integral of what is the divergence The divergence is what I found in part A. 3x squared plus 3y squared plus 3z squared dv. What is my shape? I have a sphere of radius 3. So let me draw my sphere. Radius 3. So I could keep this in Cartesian coordinates, like our regular coordinate system with x, y's, and z's, but that seems a little bit hard, right? I have to then like solve for z, solve for y, solve for x. There's going to be lots of square roots. I don't like square roots. So let's convert to spherical coordinates. And the point of learning all those coordinate changes was so that we can make our integration problems much nicer to compute. So by converting to spherical coordinates, what happens? First of all, what is the equation of our sphere? Or like, what is something we know about spherical coordinates? We know x squared plus y squared plus z squared equals rho squared. That was one of the like formulas. What is the equation of my sphere? You should know an equation of a sphere is x squared plus y squared plus z squared equals 9, because my radius is 3. So I have equals 9 here. So when I convert to spherical, what happens? 3 things: bounds, integrand, differential. Let's work with the bounds first. What are my bounds going to be? The bound, imagine drawing a line radially outwards, meaning going outwards. Rho starts with 0, because that's like the origin there. What is the radius of my sphere? The radius of my sphere is 3. So my rho goes to 3. You can also see why the upper bound should be rho equals 3 by looking at the equation of our sphere. If I converted my equation of the sphere to spherical coordinates, I get rho squared equals 9. In other words, rho equals 3. So that's why the top is rho equals 3 as well. What are my phi bounds? I have no limitations. I have my entire sphere. So what is the like greatest range of phi I can have? Well, phi represents the angle you make with the positive z-axis. So I start at 0 because if I'm at 0, I'm still in my region. I'm still in my sphere. Then I go all the way down. The maximum I can go is like the maximum ever is always 180 at most. So pi. Sometimes it's less than 180, depending on what you're, like if you only had a hemisphere, your phi would go from 0 to pi over 2. But because we have no limitations, we have our entire sphere, we have 0 to pi. And then theta, again, no limitations, so 0 to 2 pi. Okay, so those are our bounds. What about our integrand? How can I rewrite this? Well, I can rewrite this as 3 times x squared plus y squared plus z squared. And what is x squared plus y squared plus z squared? That's rho squared. So I have 3 rho squared. And then what about my differential? When I convert to spherical, it gives me rho squared sine phi. D rho d phi d theta. Okay, and this requires a lot of integration. I'll let you guys do it. I get an answer of this. 2/1916 over 5 pi. So I have a question in the chat. Should we memorize the spherical equations? I would recommend looking at the study guide. Not sure if it says you have to there. Okay. And yeah, so generally, so question is that, will we ever need to use the left side of Gauss's formula? And are the bounds per Gauss always the formula for the boundary of the surface? So usually in a question like this, when you're using Gauss's formula, the idea is that they want you to use the right-hand side because they want you to show that like, you know, how to take the divergence and then like, what is the surface that we're working with. And so when you're doing the triple integral of the divergence, the bounds for these should always be based on what your object is, what your closed 3D object is. And here it's a sphere. So that's why for my bounds, I'm doing the bounds for a sphere. And whenever you're using Gauss's, you should always have a closed 3D like shape. So like if you only have a hemisphere without the lid, there's no lid, it's just like a bowl, you can't use Gauss's. But if you do have a lid, so it's like a closed bowl, then you can use Gauss. I haven't really seen using the left-hand side for Gauss. What does the circle on that double integral mean for Gauss's theorem? This is just like one of the notations I used, which is, it's just saying like, you have a closed shape. But you can use the notation that Bryce also uses, which is also fine. Okay.
Can we use the second part of Gauss where we find the derivative of the one form?
Yes, you also can do that. So you would, to do that, you would have to like rewrite your function first. So like it's x cubed plus y cubed dy dz, all that stuff. Wait, well, okay, if you do it that version, that would be like the longer version. Like that would require a lot of like, you have to parameterize your sphere, and then you might need a d sigma, like a surface area integral. So yeah, in this case, because they like give you it in the vector form, I would recommend this is like the quickest way to do it.
How do we know when to use which form of Gauss?
If they give you the original vector field in a like an IJK form, you should just do the divergence, because we know how to do the divergence of some vector field. If they give it to you with like the wedge stuff, then you can use the derivative formula for Gauss, which is like this dv. Okay. I think I think it really depends on what you like, what works better for you also. I think most of the questions I've seen are always using this way because it's much faster. Like you see, we just took our function, took the partials, and then we just had to figure out the bounds. Okay. Part C. Wait. Okay. If the hemisphere is not closed, how do we calculate flux? So if the hemisphere is not closed, so I'll call the bottom part like the lid, and this top part is the cap. The cap has a boundary of S, lid has a boundary of S prime. What you do if you're trying to find the flux over just the cap. This requires you pretending like it would be nice if this hemisphere was closed, right? Because if it was closed, we could use Gauss's theorem. Gauss's theorem, let's pretend it's closed for now. Gauss's theorem says that the triple integral of S with the lid is going to go in the opposite direction, a negative direction. The reason this negative is there is a little bit to do with orientation. Like our cap goes one way and our lid is going to go the other way. Don't really have to know the derivation of this. What's another way to write this? Triple integral of S plus triple integral of the negative S prime. Because doing a union is almost like adding. What's another way to write this? This is S. Now I can take out this negative sign and say it's minus triple integral of S prime. So I have the triple integral over the entire shape, imagining that it's closed, is equal to this. But the original question would have been to like find the flux over just S. And we see that we do have that flux over S part. So I can rewrite this and say triple integral of S equals the whole thing plus triple integral over the lid. So if you're just finding flux over the cap part without the lid, you can imagine that it's closed and use Gauss. Then you add it with the flux over the lid part only, and that will give you your answer. Okay, and this was just like an aside question. Okay. So to calculate flux over the lid, is that using Green's? Yes. So to calculate flux over the lid, you can use Green's or Stokes. Okay. Part C, what is the flux of the curl of F across this same sphere? Okay. So let's think about this. Oh, okay. What am I computing? Flux of the curl of F. So part C, I'm trying to find flux of curl of F over sphere. Okay. In general, if we have a closed shape like a sphere, what does Gauss's theorem say? Gauss's theorem says that the integral of f dot n d sigma equals, so I'll write, this is how it's written in the videos, right? This is the formula for Gauss's theorem for the vector language way. This is the formula. This is flux over, let me call it G. This is G.
Like maybe like the first or like one of the main be like dedicated for
So Gauss's theorem says flux over some G is this. Right now, we're trying to ask flux of curl of F. So imagine this whole thing, let's call curl of F, let's call it G. So that means that we're trying to find double integral of what is G. We're considering it as the curl of F right now. Curl of F dot n d sigma using the formula, the red formula. So I'm substituting G for curl of G. Curl of F, sorry, curl of F. D. Right, this is divergence theorem for a closed shape. I have a closed shape, so I should be able to use Gauss's formula, Gauss's theorem. Right now I'm trying to find, Gauss's theorem says flux over G, but I'm trying to find flux over curl of F. So let's consider G as curl of F. Plug in curl of F everywhere I see a G. That means I get this formula. Then what is this? This is divergence of curl of F. We know that the divergence of a curl of F is always 0. Wait, I think my internet is slightly lagging. Can you guys see this thing in blue that I wrote? Or not yet?
No, we can't.
Okay, so it's like slightly. Okay, so but what is the divergence of curl? It's 0. So we get that. This exact answer, 0.
So why would you not do Stokes for this?
Yeah, you wouldn't use Stokes because we have a closed 3D shape. And if you have a closed 3D shape, that means you should use Gauss's theorem. And so the idea is like, this is saying that if you are doing flux of the curl over some closed thing, you'll always get 0. But in general, like how come when we use Stokes' theorem, we don't always get 0? Stokes does not always give 0. It's because we don't always have like a closed 3D thing when we're doing Stokes. Because what is Stokes? We always use it when it's saying like flux of curl. But we don't always get 0 as our answer, right? We get like some random number. But because in this question, we do have like flux of curl, but it's over a closed 3D object, that means that flux of the curl will be 0. And the like intuition behind why that is because of Gauss's theorem. Because once we have a closed thing, we can use Gauss's theorem.
So you need to have a closed shape for Green's and Gauss, but we don't have to have like a closed shape for Stokes, right?
So you don't need to have a closed thing for Stokes.
So when would you use Stokes? Like, when are you sure that you can use Stokes?
So if it says flux of the curl over like some surface, then you can use Stokes. The only reason this problem was different is because they say like I see flux of curl, and yes, generally I see flux of curl, think Stokes. But because this is over some sphere, this is a closed sphere, that means I can use Gauss's theorem.
Let's see if we force our way through Stokes, will we still get 0?
You should still get 0, yes.
Sorry, I guess this is more of just like a conceptual thing, but why is it that when we do this over a closed shape, that it's equivalent to the divergence of the curl?
That's because we use Gauss's theorem, and Gauss's theorem says that if we're trying to do the integral of, if we're trying to find the flux of something, then it's the equivalent to the triple integral of the divergence of it over the entire shape. Now we're
Oh,
doing
yeah,
the
I
flux
see.
of, yeah,
Yeah,
so
okay, thank you.
the flux of something, but our something is like the curl. Okay. I guess like you can, so you use Gauss's theorem, we get to this part. If you wanted to, you could further like say, like, we can, no, I'll just stop it. Yeah, I don't want to keep. Okay, so why is there a G dot N for Gauss? That's the formula for Gauss's theorem. It has, yeah, this is just Gauss's theorem from the videos. Final answer for part B, that was, yeah, 29/16/5 pi. Okay, any other questions on 5? Yes, this is being recorded. I hope. Yeah. Okay, so in general, Stokes does not always give you 0, right? We've seen questions where you use Stokes and you get like a number. In this case, we only get 0 because we have a closed shape and we're doing flux of the curl. If you're just doing in general flux of something using Gauss, you don't always get 0 as well. So in general, flux of curl, if you're doing Stokes, doesn't always give you 0. And just flux of something using Gauss does not always give you 0. But if you're doing flux of curl using Gauss, because you have a closed shape, or closed 3D shape, then you do get 0. Okay. All right. Question 6. So considering the following form fields in 3D, so now we have the forms language now. Of what vector field is alpha the one form, worth one form? Write your answer on paper using IJK notation. So they're saying that we want to find the vector field, which is why, well, how do we write vector fields? We always use like the IJK notation, right? So part A, alpha, this is always like, what is the field that alpha corresponds to? Or like, how do you write that field? It's always you take the same components, but instead of the D variable stuff, you write IJK. So whatever's in front of dx, that's my I component. So I have my field is xy I. Then I have z squared, dy should be j. And then I have yz, dz is k. So that's the field that it's associated with. Okay, and then part B, compute and simplify the derivative. Okay, so what is the derivative of beta? Well, beta is, so I'm just going to rewrite what beta is. Okay, and I can take the derivative directly. So any variable I see, I want to take the derivative with respect to that variable. So I see a z, So I'm going to take the partial with respect to z, which gives me 1 dz. And then I add on the other wedges. Now I see an x here, so let me take the derivative with respect to x. That derivative is negative 3 dx. And then I add on the other wedges. So dy dz. Now I see that each of my wedges have 3 variables in x, y, z, x, y, z. So I can go a step further and try to simplify this a bit. What happens, so like, let's try to get it in the dx, dy, dz form. So what am I going to do here? When I switch two things, a negative sign comes out. So I get that. But then when I switch these two things, another negative sign comes out. So negative, negative is positive. Dx wedge dy wedge dz. And so this d beta continuing is 1 dx wedge dy wedge dz minus 3 dx wedge dy wedge dz. 1 minus 3 is negative 2. So this is my derivative. Okay. Part C, compute and simplify this wedge product. So alpha wedge beta. So let me write what alpha is. Alpha is y dx minus d squared dy plus y z dz. Okay, so I'm doing part C now. Alpha wedge beta equals this thing. Wedge beta. Beta is z dx wedge dy minus 3x dy wedge dz. So how do we do a wedge product? It's almost like you're foiling. So that's what we're exactly going to do. Imagine foiling everything. We take this first expression, multiply it by that. We get xyz dx wedge dx wedge dy. The order matters here. So whatever is on the left side, I have the dx first, and then I wedge the other things, dx wedge dy. And then I have this thing multiplied by that, which gives me negative 3x squared y, dx wedge dy wedge dz. Okay, and I keep foiling. So this term times this term gives me minus z cubed dy wedge dx wedge dy. This with the last term gives me plus 3x v squared dy wedge dy wedge dz. Finally, the purple gives me plus yz squared dz wedge dx wedge dy minus 3xyz dz wedge dy wedge dx. Now some things cancel out because if we have two variables repeated in the wedge, it cancels to 0. So here I have an x and another x. So this is 0. Here I have a y and a y. So this also becomes 0. What else? Here I have a y and a y. So this becomes 0. And anything else? Here I have a z and a z. So this also becomes 0. So what I'm left with is the blue thing, negative 3x squared y, plus the purple thing. Now again, I can simplify this a bit if I wanted to by making it all dx dy dz. So what happens when I change this up? I know that a negative sign comes out if I swapped these two. Then another negative sign comes out if I swap, so it stays the same. So I have the blue thing plus the purple thing. So my final answer is negative 3x squared y, yz squared, dx wedge dy wedge dz. Okay. Final part is what is the integral of beta over a unit disk? Write your answer below and show your work. Hint, do this directly. Don't use Stokes, Gauss, or Green's theorem. So this is an example of integral of a form, right? Integral of beta. What is beta? So beta is z dx wedge dy minus 3x dy wedge dz. And there's no like, usually in a 2 form, I always have a dz wedge dx term, but there is none. So I'll just write it as 0. Okay, so I'm doing the integral of this 2 form. How would you normally do it? Step 1, you would parameterize your surface. Plug in your parameterization into your integrands. So whatever z is, I plug it in here. Whatever x is, I plug it in here. And then what do the wedge products mean? So parameterize, plug it into integrands. And then for the wedge product stuff, wedge products represent area projected to that plane. And so from my parameterization, I would take like the derivative. So let me say parameterize like that. I would calculate what is dg, and then take x and y numbers from dg. Okay, but in this case, let's look a bit carefully about the question. They're saying find the integral over the unit disk in the xy plane. So we have a unit disk in the xy plane. So I just have a disk in the xy plane. So let's look. If I parameterize this disk, how would I parameterize it? I would parameterize it like g of xy is, I need an x component. So let me make it very abstract. We're trying to parameterize this lid. So we'll have something in the x component, right? We always have an x value. We'll always have something in the y component. But what is z? We have a flat lid in the xy plane, meaning z is always 0, no matter what. So it doesn't matter what I parameterize it as. Let me just focus on the fact that z is always going to be 0 because it's a flat unit disk. So because z is 0.
Know it's a flat unit disk.
What? Sorry.
How do you know it's a flat unit disk?
Yeah, because they say it's a unit disk in the xy plane. And xy plane is the same as saying.
Oh, okay.
Okay. So that means that what happens? What were my steps, right? I have my parameterization. I plug it into my integrands. That means when I plug it in for z is 0. Right? So I have 0 times something, times whatever this determinant is. And then I have minus 3 times whatever my x parameterization is, leave it question mark. But what is dy wedge dz? That's the area projected to the yz plane. Do we have any area projected to the yz plane? We don't, because we only have a flat disk. So if you imagine like squeezing it to the yz plane, you don't have any area. It's just like a line in the yz plane. So this is 0. And then you have plus 0. So this integral is going to be the integral of 0 minus 0, which is 0. Okay, any questions on 6?
I have a quick question. If you were to parameterize this, what would your like values for f and t be?
So I would. So this is a circle in the xy plane. So it's like x squared plus y squared equals 1. So I can keep it as, let's say, so what would happen? Okay, let me think. So x is 0. So I have x and y. I would say it's cosine of, let me see, r and theta. R cosine theta, r sine theta. Where r would be essentially 1.
Okay.
And if you were to solve this, would you like, how would you plug this in? So would z just be 0 and then dx wedge dy would just be dx dy? How would like plugging that back in look like?
Yeah, so you would find like your derivative of g. And we could, yeah, so derivative with respect to r is cosine theta, sine theta 0, negative r sine theta, or cosine theta 0. So for like the dx wedge dy part, you would take the x and y components from your derivative. So the x components are that first row. So you would have cosine theta, negative r sine theta, ln sine theta, r cosine theta. And take that derivative, or determinant, sorry. Okay. Problem 7. So we want to consider the joint probability density function. So we have density is 6e to the negative 2x minus 3y. And part A says for a point chosen at random with this density, what is the probability that x is greater than or equal to 1 and y greater than or equal to 2? Okay. So let's first kind of draw out what's happening. We have a plane. X has like 1, 2, 3, y 1, 2, 3. And we're trying to find the probability that x is always greater than or equal to 1. So we have x always greater than or equal to 1. Y also has to be greater than or equal to 2. So we're looking at what is the overlapping part. We want to find the probability that we have a value over here.
Oh, wait.
Okay, so we have the double integral of how do we find probability? Probability that x greater than or equal to 1 and y greater than or equal to 2 equals. Well, to find the probability, it's always rho dA. For rho is my probability density function. So I have, what is my rho? It's 6 negative 2x minus 3y dA. What are my bounds going to be? Well, let's say I do dx dy. You can also do dy dx, doesn't matter. So what is x going to be? X goes from 1 to, it could keep going. It doesn't have a limit. So it goes from 1 to infinity. Y also has no limit. It just has to be greater than or equal to 2. So I have y from 2 to infinity. Okay, and I'll let you guys calculate that. And I got 1 over e to 8. What about part B? It says, how would you compute the probability that x less than 1 or y less than 2? So this one, the wording is slightly trickier. So the probability that x is less than 1, that is like, okay, let me draw a new like highlighting thing. X less than 1 is all of this part. Y less than 2 is this part. But it could also be like both. Like or means like you could have this or both of them. So we still want to count this part as well. So part B, what does this mean? We want this entire region. They're asking what is the probability that we have this highlighted part, everything. Well, in part A, we just calculated what this red part is. So the probability that x is less than 1 or y less than 2 is going to be, what's the maximum probability I can have? It's like 100% or 1 minus the probability that I just found in part A, which is 1 over e to the 8. Okay. How did you get that x and y each go from 0 to 3 on 0 to maybe that's 0 to infinity on the graph? So we got, how do you calculate? Okay. So we know that the bounds are going to be like 1 to infinity, because they say in general, our domain is just that x greater than or equal to 0, y greater than or equal to 0. So the domain we're considering is just the first quadrant. So I have this entire first quadrant. Then in part A, we're just finding probability that x greater than or equal to 1 and y greater than or equal to 2. So that's this entire red region. And so let's see. So some people want to see how we integrate a bound to infinity. So that's like from single calc where you do like the limit, depending on how you learned it. Like you can do limit as b approaches infinity of x equals 1 to b of 6e to negative 2x minus 3y dx dy. So I get y equals 2 to infinity of, okay, let's see. So I have, this is going to be 6e to negative 2x y over negative 2. Yeah, from 1 to b of limit as b goes to infinity dy. So the reason I didn't have to do, like you can do use substitution and stuff, I kind of just guessed that it's negative 2 because what happens, I have this thing, if I take the derivative of it, I do get this integrand. That's just a faster way. And hopefully I did it correctly. So we have limit as b approaches infinity of negative 3e to negative 2b minus 3y minus negative 3e to the negative 2 minus 3y dy. Okay, what's another way to write when I have negative exponents? So I have limit as b approaches infinity of negative 3 over e to the 2b plus 3y. Right, if I have a negative exponent and I want to bring it to the denominator, the negative disappears. Plus 3 over e to 2 plus 3y dy. Okay, so I have y equals 2 to infinity of. What happens when b goes to infinity? When b goes to infinity, this denominator is very large. And we know that if you have the limit of some number over infinity, that gives you 0. This is 0 plus 3 over, there's no b's here, or like I already plugged in the b's for 1. So I just have a constant here. Okay, and then from there, you should be able to integrate with respect to y and do the same thing. Okay. Question, why don't we subtract the part where the two areas overlap? Or part B, I'm guessing. We don't subtract this part because at this part, you still have like x, you still have one of these things. And like it has to do with like the wording of how they, like just the or wording. So it's like you could have one or the other or both is like what this means. So that's why we don't need to subtract anything here. What if the problem asks for x less than 1 and x less than 2 instead of or? If they said they wanted x less than 1 and y less than 2, then the only region where that happens is this intersecting region. So you would want to find the probability that you're in this rectangular intersecting region. And so you would have integral of, well, x has to be at least greater than or equal to 0. So the bottom bound for x is still 0, but you only want it to be less than 1. So the upper bound would be 1, and y would still be from 0 as well, In the upper bound, we want it less than 2. You put 2. That's an aside. Okay, any other questions on 7? Okay. Let's go to 8. So 8 says, consider the unit density solid body given by x squared plus y squared less than or equal to z, where z is going from 0 to 4. Okay. Part A, compute the z coordinate of the centroid. Okay, what is the formula for centroid? The z coordinate of the centroid is, we have, what are we in? We're in 3 dimensions because we have x, y, and z. So I'm going to have a triple integral of, because it's the z coordinate, I need a z in there, dv, rho dv, over triple integral of 1 rho dv. That's the formula for centroid. Now, because they say we have unit density, the rho, that means that rho equals to 1. So now my formula becomes triple integral of z dv over triple integral of 1 dv. Now, what is the shape of my thing? I have this x squared plus y squared less than or equal to z. What does that look like? Well, maybe I don't know what the shape is, but I can kind of test what it might look like, right? Z goes between 0 and 4. So let's imagine what happens when z is 0. That means that our equation becomes x squared plus y squared less than or equal to 0. What is that in my picture? In my 3D picture, x squared plus y squared less than or equal to 0, that's like a circle almost of radius 0. Circle of radius 0 is just like a point. Z could be, what if z is 2, right? Z is allowed to be 2 because it's between 0 and 4. If z were 2, that means I get a circle of radius square root 2. So at z equals 2, I have some circle of radius square root 2. So I get this circle. And z, what if z is 4, right? It could go all the way to 4. Then I get x squared plus y squared less than or equal to 4. That's a circle of radius 2. So when z is 4, I have a circle of radius 2. So this is just the intuition, but we have lots of z values. So at each z value, I have a circle of some certain radius. So that means that my 3D picture is this paraboloid, which I didn't draw very well. But yeah, it's a paraboloid where at each z level, you have a circle of different radius. Okay, so we have this paraboloid. We're trying to compute this integral. I can keep it in Cartesian coordinates again, but let's not do that because that would be hard. I have to figure out what's the equation of this, do like square roots and stuff. Right, let me convert to, what should I convert to? If I have a paraboloid-like thing, let's try, and you have like a flat thing at the top. Let's try cylindrical. So what does cylindrical coordinates say? We have triple integral of z dv. Okay, in cylindrical coordinates, z is still z, like those were the cylindrical to Cartesian coordinates formulas. Z is still z, so I can keep that. So I've changed my integral grand. What else do I need to change? I need to change my bounds, and I need to change my differentials. My differentials, dv, when I convert to cylindrical, I get r dv dr d theta. What about my bounds? Well, my bounds are, where does z start? How do I get the z bounds? Well, to get the z bounds, what do I always do? I draw a line in the increasing v direction. So I have that green line. Where does z enter? It enters at x squared plus y squared. How can I rewrite x squared plus y squared in cylindrical coordinates? Well, in cylindrical coordinates, x squared plus y squared is r squared. So z enters at r squared. Where does it exit? Well, it exits at whatever this flat plane is. What is that flat plane? That's the z equals 4 plane. So exits at 4. Now that I have my z bounds, I can imagine collapsing the z-axis. When I collapse the z-axis, what do I get? I get a circle of radius 2. I get that top circle once I collapse it down, right? And what is the bounds for those? Well, r goes from what to what? It starts at 0. What is the radius of this circle? It's 2. So it goes to 2. What about theta? Well, I have my entire circle, no limitations. So theta is 0 to 2 pi. Okay, and the denominator has the same exact bounds. R squared to 4, 0 to 2, 0 to 2 pi. But now the integrand is just 1. R dz dr d theta.
Sorry, why isn't the bounds for z just from 0 to 4?
Yeah, it's not 0 to 4 because to get my z bounds, I always draw a line in the increasing z direction. So I'm drawing this line here, this green line. What curve does it enter first? It enters this curve. If you wrote 0, well, this line, this green line doesn't always enter at 0. It would only enter at 0 if I drew this specific green line. But I'm allowed to draw these green lines anywhere I want, as long as they're in the positive increasing z direction. So the lower bound can't be 0. It has to be like, what happens if I draw the green line here? It enters at whatever this curve is, not 0. Another way you can see it is like, if I said v equals, say, 0 to 4, that's assuming that my shape is a cylinder. Because in that case, when I draw a line in the increasing z direction, what surface does it enter? It enters the bottom z equals 0 plane, and it exits the top z equals 4 plane. But we don't have a cylinder, we have this paraboloid. That's an aside. Okay. If it's if it's given to us that z is between 0 and 4, why can't, yeah, so that was this. Why can't we say z is the 0 is the lower bound? It's because we don't always, like the lowest value that you can have in your region is not always 0. Like over here, the lowest region is not 0. It's like whatever number this is, like 2 or something. If you were to say z equals 0 is the lower bound, that's implying that your shape is a cylinder, because the z equals 0 plane is this flat thing. Okay. Part B, write down the moment of inertia, di, for this body if it is rotated about the x-axis. Okay. What is the formula for moment of inertia? Actually, what am I? Oh, I'm just writing the moment of inertia element. Okay. So moment of inertia element is always r squared rho dv. What is rho in my case? Rho is 1 because I have unit density. Okay, so right now I'm looking at r squared dv. What is r? R. What is r? That's the distance from any point, xyz to the axis that I'm rotating about, to axis of rotation. So I look at my shape. Oh, and yeah, the final answer for part A, by the way, was I got 64 pi over 3 on the top, ln 8 pi on the bottom, which gives me a final answer of 8/3. Okay, so back to this. What is the distance r? Well, I look at my shape. I have some random point. Also, let me label my axes. Okay, so I have some random point. Let's say x, y, z. And I'm rotating about the x-axis. So what is the closest point on the x-axis that I have to my random point? Well, the closest, like the point with closest distance would be the point that has the same x value, but zero is for y and 0 for x or z. So like you're always finding the distance from some random point x, y, z to some axis that you're rotating about. The closest point that you have to that, the closest point on the axis of rotation that you have to the random point will have the same value in the, like whatever axis you're rotating about. So now I have my 2 points. What is the distance formula between 2 points? I always do x minus x squared plus y minus 0 squared plus z minus 0 squared. That means it's square root of y squared plus v squared. So I have my radius, or sorry, my r is square root of y squared plus z squared. But I have r entirely squared dv. So my moment of inertia element is going to be y squared plus v squared dv, because the square root and the squareds cancel out. Okay, question, why do you take the density into account when you compute the centroid? That's the formula. For centroid, you always have density in there. The center of mass does not have density in the formula. Okay, and question, can you explain once more why you took an x for the second coordinate? Isn't the radius usually x squared plus y squared? So r here is not radius, r is distance, and it's usually x squared plus y squared in other problems we've seen, because in those cases, we're rotating about the z-axis. About z-axis. So if we're rotating about, if we were to rotate about the z-axis, what would we do? We would find the distance between some random point, x, y, z, and you would have the same z value, but 0 is otherwhere. And so the distance would give you z minus z squared plus x minus 0 squared plus y minus 0 squared, which is why usually we have like a x squared plus y squared for our distance. But because we're rotating about the x-axis, we eliminate that x. So we're only left with y squared plus z squared. Okay. Wait, so centroid is the one, let me look real quick. It's centroid. So this was, so maybe I recalled it. Let me just check. Centroid. Yeah, sorry about, yeah, okay, sorry. So centroid is the one without density. Okay, so you can ignore these. Yeah. So sorry, centroid is the one without density, and center of mass has the density. Yeah, thank you. Okay, what would this R look like for a cylinder versus a paraboloid? It would be the same thing. Y squared plus R squared would be y squared plus z squared, because imagine you have this cylinder here. We would still take some random point x, y, z. And if we're rotating about the x-axis, well, the closest point to the x-axis would have some like the same x. Like you're finding the distance from that to same x, 0, 0. So like here's, or like, let me imagine you have this axis. The closest point on the axis of rotation that you have to XYZ would be like right here. So imagine this x-axis is extending in the back. What is that distance? Has the same x value, but y is 0, z is 0. So distance is still square root of b minus 0 squared plus y minus 0 squared plus x minus x squared. Okay, and yeah. Oh, wait, we still have another question. Okay, question 9. Okay, your goal is to evaluate the following integral, and we have the domain of integration D is the region in the positive quadrant given by those things. Okay, and come up with a good coordinate transformation from UV to XY, which makes the domain into a rectangular rectangle in the XY plane, and write this coordinate transformation. So here the reason this question might look a little bit confusing now is because they've switched up your lettering. So don't be confused by the change of lettering. Right now, imagine U and V are your standard like letters, and you're trying to transform it to X and Y. We always do the same process. We kind of look at the bounds that they give us. We try to rename create some name so that the bounds are between two numbers. And they gave us very nicely what they should be. So I'm going to name X to be V over U. So I'm going to say part A, I'm going to call X V over U. Because in that case, my X bounds are going to be exactly what they wrote, 1 to 3. And they also gave me this. So why not just call UV Y? So if I call Y UV, then my Y bounds are going to be what they gave me, 1 to 2. And this makes a rectangle in the XY plane because what are these bounds? What do these bounds look like? That's if I have this plane and this is X, this is Y. X goes from 1 to 3, Y goes from 1 to 2. And so this is exactly a rectangular region. Okay. Part B, use this to transform the area element, showing work on your paper, below in the form x, y, x, dx, dy. So what does that mean? That means they want you to use the change of variables formula to transform dx, dy. What does change of variables formula say? It says dx, dy is the absolute value of the determinant of this Jacobian matrix, du, dv. That's by change of variables theorem. Okay, and let's see what we have. Do we have x equals something, y equals something? We do. So we can exactly take this Jacobian. So what is the absolute value of the determinant of this Jacobian, where we take our first output, which is v over u, and we write it as v inverse. And I take the partial with respect to u. Partial with respect to u gives me negative v u negative 2. Partial with respect to v gives me u to the negative 1. And then I look at my second output in my second row. Second output is y equals uv. So what is the partial with respect to u? That's v. Partial with respect to v is u. Du dv. What is that determinant? Well, that determinant is negative v over u minus v over u du dv. And this is dv. Right, so this is absolute value of negative 2v over u du dv. When I take the absolute value, this becomes positive 2v over u du dv. So this is my change of variables, what my change of variables formula says. And yes, these are only the first, like you take the partials once. So in other words, this is the notation for the Jacobian matrix or your derivative matrix. So this is saying take the determinant of the Jacobian. Okay. Part C, evaluate the integral. What is the integral? We're doing the integral of u squared v squared. Okay, double integral of u squared v squared du dv. That's what they are asking us to find. But we want to transform this into a dx dy question. So let's see, what are the things we need to change, right? We always need to change bounds, differentials, and integrands. Okay. Let's look at the bounds. So if I change the bounds, what are my bounds going to be? Well, I look at part A. I already have that x is 1 to 3, y is 1 to 2. So those are the exact bounds I'm going to use. X is 1 to 3, y equals 1 to 2. Let me keep the integrand like this for now. Sometimes it works out very nicely that whatever's in your integrand, you can immediately write in terms of x's and y's. But other times you might want to first write your differentials and see if anything like cancels out so that things work out better. So let's keep it like this for now. What is du dv? Well, up here in part B, I found dx dy equals that, but I don't want a 2b over u du dv. I just want what is du dv. So let me divide both sides by 2b over u. So I get u over 2b dx dy equals du dv. That's from part B. So now I can substitute. This is u over 2b dx dy. And let's see if anything cancels out. Well, we have a b canceling out. Right, so let's look back at what our x's and y's were. Let me copy this. Actually, you may not even need to cancel stuff out. Okay, we can keep it like this. So let's see, can we write this in terms of x's and y's? Well, we see a ub here. So, and we see a u squared v squared. So maybe this part looks like y squared, right? Because y squared is u squared v squared. Okay, but what about this part? This part is a little bit off. We have u over v, but x is v over u. But what can we do? It's kind of like we have the reciprocal, right? So what if 1 over x would be u over v? And that's exactly what we have. This is 1 over x. So that means that my integral is now y equals 1 to 2, x equals 1 to 3 of u squared 1 over x, but don't forget that 2 there, dx dy. Okay, and you can compute that integral, and I get 7 natural log 3 over 6. Okay. Any questions on problem 9?